and is honestly incredibly complicated. So let's simplify it. We'll remove a few of the layers for now and step through the basic principles of how we generate an electromagnetic wave that propagates out from this antenna. To start, at the bottom we have a microstrip transmission line feed coming from one of the small microchips. This transmission line feed is just a copper PCB trace or wire that abruptly ends under the antenna stack. We send a 12 gigahertz high-frequency voltage or signal to the feed wire, which is a voltage that goes up and down in a sinusoidal fashion, going from positive to negative and back to positive once every 83 picoseconds. 12 billion times a second, or 12 gigahertz. Note that high-frequency electricity works differently from direct current or low-frequency 50 or 60 hertz household electricity. For example, above the copper feed wire, we have a copper circle with notches cut into it called an antenna patch. With DC or low-frequency alternating current, there wouldn't be much happening because the patch is isolated. But with a high-frequency signal, the power sent to the feed wire is coupled or sent to the patch. How exactly does this happen? Well, as mentioned earlier, a 12 gigahertz signal is applied to the copper feed wire. When the voltage is at the bottom of its sinusoidal, or trough, we have a concentration of electrons pushed to the end of the feed wire, thus creating a zone of negative charge, which corresponds to the maximum negative voltage. This concentration of electrons on the tip of the wire repels all electrons away, including the electrons on the top of the patch, and as a result, these electrons are pushed to the other side of the circular patch. Thus, one side of the patch becomes positively charged, while the other becomes negatively charged, thereby creating electric fields between the patch and feed wire, like so. However, when we reverse the voltage to the copper feed wire 42 picoseconds later, we have a concentration of positive charges, or a lack of electrons at the end of the wire, and thus the electrons in the patch flow to the other side. The voltage in the patch is flipped, and the direction of the electric fields are also flipped. Because the feed wire voltage oscillates back and forth 42 picoseconds between one peak and trough, the electric fields in the patch will also oscillate as the electrons, or current, flows back and forth. If we pause the oscillation, we can see some of these electric field vectors, or arrows from the patch, are vertical, and because they're equal and opposite, they cancel out. However, other electric fields are horizontal in the same plane of the patch, and are called fringing fields. These fringing fields are in the same direction, and thus they add to each other, resulting in a combined electric field pointing in this direction. At the same time, electrons flowing from one side of the disk to the other, which is an electric current, generate a magnetic field with a strength and direction, or vector, perpendicular to the fringing electric field vector. As a result, we have an electric field pointing one way and a magnetic field pointing perpendicular to that. Let's move forward in time to where the voltage on the feed line becomes positive. And now we're at the peak of the sinusoid, 42 picoseconds later. The charge concentrations, or voltage, as well as the current, is all flipped, and thus the electric and magnetic fields point in the opposite directions. Electric and magnetic fields propagate in all directions, and by creating these oscillating fields, we've generated